Good evening. Today is supposed to be your last lecture for chemical bonding. And last lecture of chemical bonding, we have just finished molecular orbital theory, in which we have predicted the molecule which is found to be paramagnetic, which molecule is found to be diamagnetic, which has more stronger bond, which has weaker bond. In today's lecture, we'll do remaining type of bonding, including van der Waals force and including hydrogen bond. They are relatively intermolecular forces, relatively weaker forces in comparison to chemical bond. But as per hydrogen bond is concerned, it's going to be most conceptual bond of chemical bonding. It will be used everywhere in organic as well as inorganic chemistry to decide properties of many molecule and compounds. So we'll start from hydrogen bonding only. As the name suggests, hydrogen bonding, obviously hydrogen has to be involved here. So the hydrogen bonding. So today's first topic related to chemical bond is let's say hydrogen bonding. So you can say hydrogen bonding is interaction between hydrogen directly attached interaction between hydrogen directly attached with highly electronegative oxygen and you can say fluorine. It is interaction between hydrogen directly attached with highly electronegative nitrogen, oxygen and fluorine, and pair of electronegative atom. So it is interaction between hydrogen directly attached with highly electronegative nitrogen, oxygen and fluorine, and lone pair of any electronegative atom. Here you can say particularly, for example, if it is, fluorine HF, fluorine consists 3 lone pair of electron, which may be represented as this, with partial positive charge on the hydrogen and partial negative charge on the fluorine. It can form bond with another molecule as, let's say, HF with lone pair of electron, another lone pair of electron and another lone pair of electron, hydrogen having partial positive charge, fluorine having partial negative charge. So it is one of the example of hydrogen bond. Hydrogen bond may be represented by this dotted line. Same apart from HF, we have another thing. Let's say in the case of H2O, oxygen consists lone pair of electron, which may be represented as this, and it consists, let's say, hydrogen atoms also. And it is partial negative, yahan partial positive hai, here we have partial positive charge. In this case, oxygen consists lone pair of electron and oxygen consists lone pair of electron. Here it is hydrogen and hydrogen atom with partial positive and partial negative charge. It can form, hydrogen bonding like this. So hydrogen. So we have one of the molecule as bonding between hydrogen. We have a compound bonding between two molecules of H2O. Hydrogen bond, I am repeating again, it is the bond, or it is the interaction between. The hydrogen must be directly attached, or it should be covalently attached with nitrogen, oxygen, green. Entity has to be the lone pair of electron of any electronegative element. Now, as per hydrogen bond is concerned, hydrogen bond is weaker bond in comparison to. Hydrogen bond is a weaker bond in comparison to covalent bond. Hydrogen bond is a weaker bond in comparison to covalent bond, and it is represented as, here you can say it's a dotted line. Hydrogen bond is weaker bond in comparison to covalent bond, and it is represented as this dotted line. We'll see many more properties of hydrogen bond, but I hope you note down the definition of hydrogen bonding. Okay, let's move further. Although origin of hydrogen bond is electrostatic in nature, although origin of hydrogen bond is electrostatic in nature, similar to ionic bond, but its behavior is covalent. So although origin of hydrogen bond is electrostatic in nature, similar to ionic bond, but its behavior is covalent, it is found to be, directional. It is found to be directional in nature. It has directional characteristic. So it is found to be direct in nature. It has fixed particular direction. For example, a water molecule can participate. A water molecule can participate in maximum 4 hydrogen bonds. A water molecule can participate in maximum 4 hydrogen bond having you can say fixed tetrahedral arrangement around central oxygen atom. So maximum 4 hydrogen bond per water molecule and fixed tetrahedral arrangement around central oxygen atom. For example, this may be, let's say, water molecule forming, it is hydrogen atom and another hydrogen atom here. Partial positive charge on this hydrogen, partial negative charge on this oxygen. So it can form one hydrogen bond by this hydrogen atom. It can form one hydrogen bond with this hydrogen atom. It can form one hydrogen bond from this lone pair of electron and hydrogen bond from this lone pair of electron. So overall, it can form 4. Overall, it can form 4 bond. 4 bond, 2 with hydrogen atom and let's say 2 with oxygen atom. And it has a fixed directional characteristic similar to covalent bond. Next, further, hydrogen bond hydrogen bonds can be divided into 2 categories. Hydrogen bonds can be divided into 2 categories, and which is, it is intermolecular hydrogen bonding. I can just try to represent in the same page only. So it is intermolecular hydrogen bonding, or it may be within the same molecule. So it is intramolecular hydrogen. In the case of intermolecular hydrogen bonding, it may be, let's say, for example, having lone pair, and hydrogen, and lone pair, and let's say hydrogen and hydrogen atom, and they can form, hydrogen with water molecule. So it is another example of hydrogen bonding. Similar to this, let's say this compound is benzene, and if it is OH is attached here, it is known as phenol. And if NO2 is attached here, this compound is known as, para-nitrophenol. So para-nitrophenol can also form, hydrogen bonding with another molecule. Its another molecule may be represented as, it is H and O, and it is NO2 is attached here. So it is NO2 is attached here, and then para-nitrophenol. So it is another hydrogen bonding. I'm repeating again, this compound is also known as para-nitrophenol. So as per intermolecular hydrogen bonding is concerned, water has intermolecular hydrogen bonding. It is hydrogen bonding between 2 molecules. Same, let's say para-nitrophenol has intermolecular hydrogen bonding. It has hydrogen bonding between 2 molecules. Similar to this, another structure may be Let's say this is the compound having, let's say, OH here, and it may have O minus and nitrogen having positive charge. So here you can just try to imagine hydrogen having partial positive charge, oxygen having negative charge. So within the same molecule, it has possibility to form hydrogen bonding. So instead of para-nitrophenol, it is known as orthonitrophenol. You can say O. O-nitrophenol or orthonitrophenol here. Similarly, you can see an example of intramolecular hydrogen bonding. This may be another compound. It is, let's say, OH, and it is double bond O and OH is attached here. So here, it is, salicylic acid. The common name of this compound is salicylic acid, and they can form both, we have two different type of hydrogen bonding here. One is intermolecular hydrogen bonding, another is intramolecular hydrogen bonding. Can be divided mainly into two categories. One is intermolecular, another is intramolecular hydrogen bonding. So due to intermolecular hydrogen bonding, melting point increases between two molecules as we have hydrogen bond. With the help of hydrogen bonding, you can explain many properties, including, let's say, you can say boiling point. So if you see in the case of, let's say, boiling point, so possibilities of intermolecular hydrogen bonding, possibility of intermolecular hydrogen bonding increase boiling point. Possibilities of intermolecular hydrogen bonding increase boiling point, and possibilities of intramolecular hydrogen bond. Possibility of intramolecular hydrogen bond boiling point. Decrease boiling points, whatever we have expected boiling point, its boiling point will be less than that of expected boiling point. For example, boiling point of para-nitrophenol. The boiling point of para-nitrophenol is much higher than orthonitrophenol. Boiling point of para-nitrophenol is much higher than orthonitrophenol. Similarly, for order of boiling point, for order of boiling point, H2O has much more boiling point. Then you can say it is H2TE, then it may be H2SE, it may be, let's say, H2S. So hydride of 16th group element, H2O has much more boiling point in comparison to others. It is due to only hydrogen bonding. So it is due to, you can say, hydrogen bond. Same in the case of HF. It has more boiling point than HI, more boiling point than HBr, more boiling point than HCl, and again due to the same reason, it consists hydrogen bonding. So HF consists higher boiling point due to intermolecular hydrogen bonding. H2O consists higher boiling point due to intermolecular hydrogen bonding. Now, apart from hydrogen bonding, another intermolecular force is van der Waals force. So they are relatively weak interaction. Relatively, you can say, weaker intermolecular force of attraction. They can be divided into three categories. Van der Waals force is relatively weaker intermolecular force of attraction. They can be divided into three categories. First one is it is permanent and dipole interaction. So it is permanent dipole interaction. Permanent dipole interaction means, for example, if it is HCl molecule, in the case of HCl, we already have dipole moment with hydrogen is going to be electron deficient and chlorine is going to be electron rich. This may be, overall electron cloud of HCl. Another molecule of HCl may be, it is partial positive charge and partial negative charge. And here in this case also, this may be a representation for HCl molecule. So between these two HCl molecule, we have to have, let's say, this type of interaction between two HCl molecule. And this interaction is known as, permanent dipole interaction. They already consist some dipole moment, both HCl molecule. This permanent dipole interaction is also known as, Keesom forces. It is also known as Keesom forces. Keesom is some scientist name. Similarly, second, apart from permanent dipole interaction, it is, induced or temporary. Induced or temporary dipole-dipole interaction. It is induced or temporary dipole-dipole interaction. Here you can see, let's say one of the molecule already consists certain dipole moment. For example, in the case of HCl molecule, it already consists dipole moment. It is H plus and Cl minus. And it can induce some dipole moment on the molecule of Cl2. It can induce some dipole moment on the molecule of Cl2 as negative pole of chlorine repel electron cloud, so it acquired partial positive charge, it acquired partial negative charge. And now the interaction between, let's say, HCl and Cl and Cl. This is nothing but, induced or temporary dipole-dipole interaction. This interaction is also known as, Debye forces. Debye force. The same Debye which give, a unit of dipole moment. So Debye forces. So van der Waals forces mainly divided into three categories. One is permanent dipole-dipole interaction. Another, second is induced or temporary dipole-dipole interaction. Third one is dispersion force. Dispersion force, or you can say it is London dispersion force. So dispersion force is due to dispersion of electron cloud. Due to dispersion of electron cloud, molecule may get, instantaneous dipole moment. Due to dispersion of electron cloud, molecule may get instantaneous dipole moment, due to which it can attract. Due to dispersion of electron cloud, molecule may get instantaneous dipole moment, due to which it can attract adjacent. It can attract adjacent molecule. Overall, this force is known as, dispersion force. Overall, this force is known as, dispersion force, or particularly you can say it is London dispersion force. So this type is between, suppose if we have, let's say, one of the iodine molecule and iodine molecule. So this is the interaction between, let's say, two iodine molecule known as dispersion force. And this dispersion force is so strong in the case of iodine, it is found to be solid at room temperature. Now, as per bonding chapter is concerned, you can see structures, few common structures of, oxide, oxy acids, of phosphorus and sulfurs also. So you can say
oxy acids. Oxy acid of phosphorus. For the oxy acids of phosphorus, so you can say phosphorus consists many oxy acids, but in all these oxy acids, central phosphorus atom is tetrahedral and sp3 hybridized. As every phosphorus atom seems to be this type. So phosphorus consists many oxy acid, and in all these oxy acid, central phosphorus atom is tetrahedral and sp3 hybridized, as every phosphorus is pentavalent, something like this. For example, if you see the structures of H3PO4, it is H3PO3 and it is S3PO2. In the case of H3PO4, every oxy acid is look like this type, and same, this may be the compound, and same, this may be the compound. That's it. S3PO4, S3PO3, and S3PO2. In the case of S3PO4, obviously we have to have oxygen, 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 and oxygen atom here. Same as oxygen, oxygen, this should be hydrogen atom here. It is oxygen, oxygen should be hydrogen atom and hydrogen atom here. So it may be, let's say, OH, OH, and OH. It may be OH and OH here, and it may be OH here. So H3PO4, another is, let's say, S3PO3, and another is, let's say, S3PO2. So if you see any other oxy acids of phosphorus also, for example, further, if you see more oxy acids of phosphorus, the corresponding structure may be, H4, it is P2O7, it may be, let's say, H4P2O6. Again, the structure of both phosphorus seems to be this type of tetrahedral only. So this may be for both phosphorus atom similar structure. We have to have oxygen everywhere directly connected with phosphorus atom. Should have hydrogen, hydrogen atom, hydrogen, and let's say hydrogen atom. I put an extra one here. So this is the structure of H4P2O7. Same in the case of H4P2O6. Every phosphorus should look like this, and you can simply say like this. It is oxygen, another oxygen atom here. It is oxygen, oxygen, and another oxygen atom here. It is OH, it is another H, it is another H, and another H here. So one molecule is H4P2O7, another molecule is H4P2O6. Similarly, another may be, let's say, HPO3 whole thrice. So it is cyclic metaphosphoric acid. So it is P double bond O and let's say OH. It is O and O. It is double bond O and OH here. It is O. It may be double bond O and OH here. And this is going to be the structure. I'm repeating again, every phosphorus should consist, let's say, this type of structure. Every phosphorus atom. So now you can draw, I hope, the structure of any phosphoric acid. Similarly, oxyacids of sulfur. So one of the acid, sulfuric acid, H2SO4. Another common acid is H2SO3. Another common acid is H2S2O3, thiosulfuric acid. And in the oxyacid of sulfur, H2SO4 may be represented as this. In the case of H2SO3, this may be the structure here. And in the case of H2S2O3, it is OH and OH. And let's say double bond sulfur. Same, even if you have to draw more structures related to, let's say it is H2SO5 and it is H2S2O8. In the case H2SO5, it is sulfur, it is O bond O, and it is O and H. It consists one peroxide linkage. And in the case of H2S2O8, it also consists one peroxide linkage as this. It is OH connected with oxygen, double bond O, and OH. The common name of this acid is, Keros acid, and the common acid, let's say Marshall acid. So Keros acid, we have Marshall acid. Oxyacids of sulfur. I hope you have noted down this. H2SO4, H2SO3, H2S2O3, H2SO5, H2S2O8. Further, you can say structures of you should know the structure of P4, you should know the structure of S8, you should know the structure of SiO2, you should know the structure of P4O6, P4O10, of P4S3. So one by one, you can see these structures also. So as per P4 is concerned, the structure of P4 may be represented as this. It is P4. Every phosphorus is forming 3 sigma bond, and they all consist 1 lone pair of electron each. In the case of S8, every sulfur forming 2 sigma bond, and it has 2 lone pair of electron. So it is the structure of S8. In the case of SiO2, every silicon is surrounded by 4 oxygen atoms. As this. So this is the structure known as SiO2. In the case of P4O6, so here you can say this structure is P4O6. In the case of P4O10, this is the structure of P4O10. And same if you see P4S3, so this is the structure of P4S3. So there may be, many questions based on the structure of these different compounds, including structure or allotropes of phosphorus, sulfur, oxides of silicon, phosphorus, oxides of phosphorus, oxide of sulfur. You will learn in more detail in another chapter. It is known as P block element or S block element. So as per chemical bonding chapter is concerned, till now in chemical bonding we have just revised few concepts, including it is concept of chemical bond, concept of ionic bond, concept of Fazan's rule. Then we have discussed VSEPR theory and hybridization state, how to predict the geometry and hybrid state. Then we have discussed something known as bond parameter, bond strength, bond length, and bond angles. Then we have discussed molecular orbital theory and resonance and dipole moment. Then we have revised some concept related to hydrogen bonding, van der Waals force. And in the last, we have seen the structure of few important compounds. So from the next lecture onward, we are going to start general organic chemistry, basic concept, basic principle of organic chemistry. So as per chemical bonding chapter is concerned, this is all about the revision related to this chapter. So next class, I'm repeating again, we are going to start general principle or basic concept of organic chemistry, general principles of organic chemistry, in which we'll do something related as naming of the compound. It is basic concept, basic reactions, basic phenomena involved in organic chemistry.
So this is all about for today's lecture. Thank you.